Hello everyone again, and welcome to this particular video. And in here we're going to be exploring a specific type of heck reactions that involves cross-coupling of organometallics and organohalides. And this kind of cross-coupling is really crucial in connecting two different species with a sigma bond with the help of various changes, mainly dealing with either what type of organometallic, specifically looking at the metal that you want to use, or what type of halides are actually required in order for you to arrive at that particular formation of a new carbon-carbon sigma bond, where you have alternate bonding, either having pi bonds in between, but mainly you have a new sigma bond formed in this particular process. So in this particular video here, this is going to be part one, and we're going to just dive mainly into what you should be able to note, which is the key ideas and components of cross-coupling. And this actually is recognizing also the general mechanism and the highlight the classes of cross-coupling, and those highlights of the cross-coupling we're going to dive into those on our next videos. So in here, the next step is highlighting the key ideas and concepts of cross-coupling, and in here we're going to look at first the chemical reaction. And in this case we have a specific form of R group bonding with a type of metal. This is known to be called an organometallic reagent, and this reagent will be combined with a specific type of halide that has an R group, which is R2 attached to it, and this organic halide, where X is either a halide or a triphthalate, and this is going to be done in the presence of a specific catalyst, mainly palladium catalyst in here. And this palladium catalyst, what it does is that it does the interesting change in that particular positioning of the reagents. So therefore we have the orange bonding with the purple, which forms a new sigma bond after the cycle is actually completed, and we form a specific salt in the process. And so in this case here, what we see is that we have a switch which leads to the coupled product being generated, and we have our metallic halide or triphthalate being produced. And this is a little bit of a visual to see what is going on with the help of the catalyst. So in this case here, we have a scenario where we have a violin selling, and this particular compound here, if present in a specific butyllithium, we actually have the switching of the metal for lithium, where in this case now take note that if this is done with a specific form of I would say organic halide, but there is no catalyst involved in here, we will not be able to perform any form of reaction in this process. However, if you use a catalyst, which is mainly a transition metal catalyst in this reaction, and we introduce that organic halide in this process here, we will actually, for the first reaction, which involves selenium, this will actually lead to the formation or using copper 1 for lithium's form of the organometallic reagent. This will lead to the formation of the same products in here, where we notice that we have our new sigma bond, which is represented as the orange, and this we will look at focusing mainly on the mechanism steps that is involved in the presence of the catalyst, in this case palladium, in order for we to be able to generate our product, which is the coupled product. So focusing on the mechanism step, first is we need to take note that the palladium catalyzed cross-coupling is involved in this step. So therefore our palladium usually starts off with the 14 electron count, which has oxidation number palladium to be 0, and then as soon as we have our specific organometallic, but not that coming up, but organohalide that starts off first, not the organometallic. We want to start off with the organohalide first, and the reason why is to be able to increase the oxidation number of palladium from 0 to +2. Therefore, in this case, by a process called the oxidative addition, we are able to achieve this particular motive, which is to create this active form of this complex. Therefore, we actually have this formation being generated, which is palladium 2 complex, and then by transmetallation, which is a new step compared to the Heck reactions where we didn't have transmetallation but we have a form of carbon metallation done. But in this step here, where we have transmetallation, which is a slow step, we actually have a nucleophile, which is R1, that will form a metal, or which is from the metal organometallic M, and this will actually be introduced into that particular complex, thereby kicking out a good leaving group, which in that case is the halide. Therefore, in this particular process here, where we have this being formed, reaction takes place within, and then our grain actually leaves and forms a form of ionic bond in a way with that particular metal. So therefore, in this case, this leads to the final step, which involves a reductive elimination, where we have the formation of our sigma bond with or between R1 and R2, which leads to the coupled product generated, and then we regenerate our palladium catalyst, which is palladium 0. So this is a key 3 steps that are required in our for way to generate a coupled product, which is, don't forget, the formation of a new sigma bond between our two R groups. So this is not requiring any form of beta halide elimination, nothing like that in this step, nothing involving carbon metallation. But in here we have a transmetallation occurring in this particular process that leads to the formation of our product. So this, take note, is important as well in terms of reductive elimination, because that step needs to be a fast process. Otherwise, this will actually lead to the formation of a beta hydride elimination. So our reductive elimination step is actually crucial and important in this particular process. So the key recommendations here is that first, in here we need to focus on what is going on in the reagents. What are the reagents that is favorable for this step? So for our oxidative addition, we require a specific organohalide. Now, for our organohalide, our R2 is restricted to substituents with the beta hydrogen atom on the sp3 carbon atom. So this means that there must be no beta hydrogen that can be eliminated. Therefore, in this case, we choose reagents that are either violin halides or allyl halides or a benzyl halide, or in this case a polyfluoroalkyl halide. And this one here has so many fluorines around, no hydrogen at all, and in this case our X is either a triphthalate phosphine, and this is actually the recommended steps that is or reagents that are suitable for achieving this particular reaction, which is called a cross coupling, that limits the involvement of a beta hydride elimination from happening, or completely eliminating that step from happening. Therefore, for our oxidative addition, in here will lead to the formation of our complex that has palladium 2 created. Therefore, for our next step, which is called a transmetallation, we have our specific organometallic that has the R group 1 attached to a metal. Now take note that the metals can be based on magnesium, zinc, copper, tin, silicon, zirconium, aluminium, or boron. So any one of these guys are actually suitable for this form of organometallic. And take note that our R1 varies in structure since the coupling is faster than the beta hydride elimination. That is one thing to take note of. Therefore, our R1, we don't really care too much about the beta hydride, because in that case we know that our transmetallation is a fast process because there is no beta hydride in our R2, which is highly linked to organohalide reagent. But our organometallic reagent, we don't really care too much about our beta hydride, so we can use varying types of organic compounds that's attached to that particular metal. So therefore, in this next step here, we have a particular metal bonding with our halide, and therefore we form a complex that actually has the two R groups positioning in that particular position that leads to the formation of a reductive elimination, which is a fast process, and this leads to the formation of our sigma bond between the two R groups, and then recreating or regenerating our palladium 0, which is going to be used to continue our particular cycle in here. So now in here we're going to look at the differences in the relative reactivity. So in here we have a specific type of reagent, and this reagent has, I would say, competing, I would say, halides. One is a triphthalate and the other one is an iodide around this aromatic ring, and in here we call it a substituted triphthalene, and in here we are going to react this with a specific compound which is an organometallic. In this case we call it an organozinc because there is a zinc that is attached to the organic compound in there. Therefore, in this case, when we perform this reaction in the presence of palladium, and that palladium is our catalyst in here, we know that this reaction here is done at room temperature, and at room temperature this actually is favoring the iodide being used to perform our specific organ or our oxidative addition. Therefore, this then results in the formation after our first cycle of our specific bonding, which is the formation of that sigma bond between the two particular R groups that are actually aromatic. So in here we have this particular yield to be 72 to 88% in terms of the yield, and then if you perform this reaction again, but this time we actually increase in temperature to around 65 degrees Celsius, this actually is favoring a triphthalate region that is going to be performing the oxidative addition. Therefore, in this case, we will actually generate our 3 rings attached to each other with 2 sigma bonds in there, and in here this actually increases slightly the yield to between 74 to 89% yield. So this is how interesting in terms of how the temperature determines which regions of that particular organohalides or which halides are actually favorable in terms of changes in temperature, or in some other cases changes in pressure. So on our next video here we're going to focus on 2 reactions that are highly linked to cross coupling, and this is mainly focusing on how evolving this particular reaction has been actually accomplished in terms of the organometallic section, and this is highly novel in terms of the Nobel Prize, and this actually started off since the early century, 20th century, in this particular year where we had Grignard actually using magnesium in the formation of a Grignard reagent in the year 1912, and then in the year 1973 Wilkinson and Fisher actually used a sandwich compound which is ferrocan, and this was actually crucial in the formation of intrinsic products in the process. And then later on in 2005 we actually had a specific reactant that is involving an archaeomethylation, and this actually is done by Covalin, Garbers, and Shawrock. And then focusing on our next two video is actually looking at these guys, Suzuki and that of Sterling, who were actually involved in the transition metal catalyzed coupling, and Heck was actually the first, and they all won Nobel Prizes except for Sterling, who died in 1989. But because they don't give Nobel Prizes to someone that is diseased, you can actually give it to someone that is actually linked to that particular research. So it was given to Suzuki instead of Sterling. And Nagashi, I can't pronounce her name, I apologize, and Heck, they all shared the Nobel Prize for their contribution to the transition metal catalyzed coupling. So on our next video we're going to focus first on Sterling, and then followed by that we'll look at Suzuki. So that's about it for this particular video. Hope you're able to understand the basis of cross-coupling, organometallic and organohalides, and what are the recommendations and the key components that is required to accomplish cross-coupling, which involves, don't forget, the bringing of two R groups to form a new sigma bond and producing a metal halide as the product when you have a specific form of either a metal that can be changed either recommendedly by you or by a specific reaction, and at different temperatures you could favor one type of halide compared to the other type of halide in this process. So that's about it for this particular video. Hope you're able to understand this. Please hit the comment down below and let me hear your thoughts, and don't forget to subscribe so as to not miss out on the next video, which is going to be nice in terms of style and that of Suzuki on the future video. All the same, stay smart as always and believe in yourselves.